The word generic means in general, not specific. It's more general, so it's called generic. I guess that's derived from the word general. Specifically in Java programming, it means that the kind of structure that you're working with, the type of it, isn't specific. It can handle more than one type. That's basically what generic programming means. You're writing programs that can handle more than one type. What we've been doing now, you have a specific type and the program handles that type and that's it. Generic programming is a different type of programming in which the program can handle more than one type. The same program can handle more than one type. So there are a number of ways in which you could do generic programming, and we'll look at several of those ways in this video. All right, let's say we declare obj, that variable, to be type object. Now you recall that object, that class, the object class, is at the very top of the hierarchy. Every class is going to be a subset of something that ultimately is going to be a subset of objects. So object is at the very top of the hierarchy. Okay, and so let's look at the next line. We have we're initializing x to 5, and then we have remember, integer all spelled out. That's a wrapper class for integer, and R is going to point to it. So we create a new integer object and we initialize it with what's in X, which is 5. So we have this wrapper class, which is creating an object, which is a box. And inside that box, you have the constant 5. All right. All right. So R is pointing to this object and we assign R to obj. Is that legal? They have different types, right? R has type integer and obj has type object. Yes, it is. Why? Because obj is way up on the top, which means after this assignment statement, obj is necessarily going to be pointing down to the integer level. All right? And pointing down is legal, right? You can point down. That's perfectly legal. And why is it legal? Well, common sense should suggest it should be legal, because integer is ultimately, it's a subclass of something, which is a subclass. Eventually, you're going to get up to object. So it is necessarily an indirect subclass of the object class, which means it inherits everything in object, right? So an object pointer, which is supposed to point to object, it's okay to assign as something that points to R, because this thing that R is pointing to as an integer will necessarily have everything an object that's created from the object class has, right? Because it inherits everything from above. All right. So we can assign obj a pointer to anything. So for that reason, it's not tied to a specific type. So that's why we call it a generic pointer. If you said integer R, you're tied to that type, right? But if you say object obj, then that can point to anything. So it's a generic pointer. All right, so here's what we get when we do the code on the previous side. We have R pointing to an integer object, right, which contains 5, and there is the variable 5, which has X in it. And we have the obj pointer, which is at a higher level, pointing down to the integer object. And that's perfectly legal. Pointers can point down in the class hierarchy. All right, so in this example, I'm going to use the generic array, and it's going to be an object array. And since it's going to be an object array, what's in that object array, every slot would be of type object, which means it can point to any other object. So that's how I get a object array. Okay, that's how I get a generic array, by just having an array whose type is object, each slot is type object. Now, this is just the first part of the program. You don't see anything having to do with object arrays here. It's just two classes, and they both have X instance data, and they both have an X display. But the X in the Q class is initialized to 2, and in the P class it's It's initialized to 1. They're just two different classes, all right? Now, if you and one is not the subclass of the other. So if you have a pointer that is type cap Q, it can point to an object created by from the Q class, but that pointer cannot point to a object that's created from the P class because a cap Q pointer is only allowed to point to um, objects created from the class 2 or subclasses of it. Okay, so we got two classes that neither is the subclass of the other. Okay, now here on line 23, we're creating a object array. And so each slot is going to be of type object. Each slot has a object pointer, right, that can point to anything because an object pointer is at the very top of the hierarchy. So it can point to any object, no matter what its type. And then we are on line 25, 26, 27 assigning pointers to those slots of the Z array. And in each one of those assignment statements, 25, 26, 27, we're upcasting, right? New P, parentheses, returns a pointer to a P object, which is, not at, and we're assigning it to the C square bracket 0, which is at the very top of the hierarchy. So that's an upcast, and same thing with 26 and 27. Line 27. Now we have a for loop that just goes through that array and displays the X data in each object. But we have to do some weird stuff there. On line 31, we have to use the instance of operator. And then on line 32, we have to do a cast on the Z square bracket I pointer. Now, why do we have to go through all that rigmarole? Well, look at the statement at the very bottom. All right, the statement at the very bottom. That's an illegal statement. And why is that? Well, what is the type of Z square bracket 0? Okay. By the way, if I used Z square bracket I, like on line 31 or line 34, it would also be illegal for the same reason that this one is illegal. So why is that illegal? Well, what is the type of the slot Z square bracket 0? Well, it's a object pointer, right? Okay. And is X display, that method, is that in a object created from the object class? No, it's not. I know the object class has a toString method and it has a equals method, but it doesn't have an X display method. So the compiler doesn't like this statement for that reason. It's, hey, this is you have a pointer pointing to an object which doesn't have an X display method, at least it thinks. In this case, in this example here, it's actually pointing down. But it doesn't know, the compiler doesn't know that you previously upcast the thing, so it's actually pointing down to an object that has an X display method. So for that reason, it will give you an error on that statement down at the bottom. So what we have to do is we have to cast it to the appropriate type. And that's what we're doing on 32. If the pointer is pointing to a P object, then we downcast to type P. If it's pointing to a Q object, then we downcast to Q. And we use the instant operator to do that. That will return true if the ZI square bracket is pointing to an object that was created from the class P. Okay? Otherwise, on line 34, you just check to see if ZI contains a pointer to an object that was created from class Q. And if neither of those is true, then for that Z square bracket I, the for loop will do nothing. Okay. So it's too bad that we have to do all this, instance of business and the casting on the pointer. But it's an easy way to get around that. And that's our next example. Oh, by the way, this is what the structure looks like. We have Z pointing to the array structure, which has a length field, which is going to have 3, and then each one of those things is pointing to an object, and the objects it's pointing to are different types, right? First one is pointing to a P object, second slot Q object, third slot to a P object. So that's a generic pointer. It can point to any object, right? Because the slots in that array have the type which is the very top of the hierarchy. So when it's pointing to any object, it's necessarily pointing either to something at its same level or down, both of which is legal. All right, now, and I already explained why this is illegal, right? Why you have, it's not, this is the way you write the previous example. You have to do all this business with instance of and casting the thing. I already, right? Okay, so I won't repeat that. All right, now here is another approach to the same problem. And this way we won't need to use the instance operator or do the casting of the ZI pointers. And what we do is we create a class R, and we just put a XDisplay method in there that will match the XDisplay methods in the P and the Q classes, okay? But we don't put anything in between the left brace and the right brace. So there's nothing going there. I just happened to put in a comment there, but there's no executable statements. It's not that I'm just not showing them. It doesn't have any in there, right? So this is the actual program, okay? And class P and class Q are both subclasses of class R. So each one of those objects that are the object created from P will have two XDisplay methods. The object created from class Q will have two XDisplay methods, one at the Q level and one inherited. Same thing for a P object, one at the P level, this XDisplay that actually has a print line, and the dummy that's inherited. All right, so now what we do is we create not an object array, but an R array, an array in which each slot is type R, right? And now we do the three assignment statements, 33, line 33, 34, 35. And what we're doing there is upcasting. We're on that line 33, for example, the new thing is creating a P object, and the type and the P class is a subclass of the R class, right? So when you do that assignment to the Z square bracket 0, you're taking that pointer to the P object and upcasting it to Z square bracket 0 because that's at a higher level. That's at the R level, which in our class is the superclass of the P level, and so you're doing an upcast. Same thing with 34, 35. So you have those 3 pointers pointing down. Those were all legal upcasts. And then on line 34, you don't have to use the instance operator or do a cast on a Z square bracket I. Now, why is that? Well, what does the compiler know about Z square bracket I? Well, it's an R pointer, right? And what method is in the R class? What method is in there? An XDisplay method. So yeah, so it views this thing as a perfectly legal invocation of XDisplay. However, when it's actually executed, it's the one that's actually defined in the P and the Q classes, those two XDisplay methods, they will override the inherited one. So when you execute line 38, you'll be executing either the XDisplay in the P object or the XDisplay in the Q object. You won't execute the inherited one. But the inherited one, even though you're not going to ever execute it, does have a important function. If you didn't have it there, then the compiler would say, hey, an R pointer points to an object that doesn't have an XDisplay, and therefore it would consider line 38 an illegal statement. All right, abstract classes cannot be instantiated. And an abstract class will necessarily have a something that's abstract inside it, right? And if it's abstract, that means it's something that you can't make an object from. Subclasses of an abstract class can be in. Oh, by the way, what the heck does instantiate mean? It means just create an object from the class. So if you're an abstract class, you can't create an object. That process is called instantiation. All right. So subclasses can be instant. You can make objects from the subclasses of an abstract class, but only if all the abstract methods that are being inherited are overridden with actual method. All the abstract methods that are being inherited are overridden with actual methods, concrete methods. Methods um, that are not abstract. All right. Let's go to the next slide. Okay, so here we're going to do this problem we've been doing repeatedly now, but with different approaches. We're going to do it another approach. We have a abstract class, and it contains one abstract method. Okay. Now, that method has the name xDisplay, which matches the xDisplay in the P and the Q classes. And the P and Q are subclasses of Picasso. Okay. Now, can we create a class from P? Can we? Yes. Even though it's going to have an abstract class, that abstract class is overridden by the xDisplay method on line 9 that starts on line 9. Okay. Can you create an object from the Picasso class? No, because it has an abstract method that's not being overridden. Right? It's just constraint. And by the way, an abstract method, look what it looks like. It's just the first line and then semicolon. It doesn't have any body. So it's just the first line. So that's an abstract method. So you can't instantiate it because it doesn't have any body. It's just you just have the head, right? Okay. All right. So let's go to the next slide. So P and Q are the kind of stuff that we've been dealing with in the previous examples, and they're both subclasses of Picasso. Okay, here we're creating an array, a Picasso array, which means each slot is of type Picasso. Okay. Now Picasso is a superclass of P and Q. So when we execute 30, 31, and 32, we're upcasting the pointers that we're getting from the new operators, right? We're upcasting. So those pointers are pointing down. That's perfectly legal. The upcast, right? The pointers are pointing down. Then on line 35, we don't need to qualify. We don't need to use the instance of. We don't need to qualify. We don't need to put cast in front of z square bracket I. Why? Well, what does what's the type of z square bracket I? It's type Picasso. Now, what kind of methods are in Picasso? Well, there's an xDisplay method. Now, that one that's actually there is an abstract one. It doesn't even have a body. But because you do have a method in a Picasso object necessarily, if one were to exist, the compiler will regard that as a legal statement. But when you execute that statement, the one that is defined in the P class or the Q class, those two will override the abstract class that's being um, inherited. So P inherits the abstract class. That has an important function because z square bracket I this statement on line 35 will be illegal. But when you execute that statement, you won't execute the abstract class. You'll execute the one that overrides it, the one that's either in the P class or the Q class. Complicated stuff, right? But it's not really that complicated, I guess. There is a logic behind it. Like Mr. Spock on Star Trek. Yeah, it's logical. It's logical. All right. All right. Now, an interface is a type of class, but it's very restricted in what it can contain, and it's used slightly differently too. contain only abstract methods and name constants. And if it does have any name constants, they can only be public, static, and final. Name constant sort of looks like a variable, but you can't change its value. So that reason uh, it's referred to as a constant. You can't change its value, but it has a name. You access it by referring to its name. Like 22 is not a name constant. It's the actual constant. We say it's the literal constant. But if you give a name to 22, if you create a name constant for 22, then that name, let's say you call it XXXX, then XXXX is the name of a constant. You could sort of use it like a variable, but you can't change its value. You can't assign it a new value. But you could use XXXX, and it would provide the constant 22. So that's what a name constant is. Now, an abstract class contain just about everything, right? If you look at that list there, just about everything. Where interface, very restricted. Now, guess what? We're going to use an interface to redo this problem again, where you have the Z array and we assign it pointers to P and Q. Okay, so here is the Z array and public void X display. That is an abstract method, right? The only thing you can have in a interface is abstract method and a named constant. So even though I didn't say abstract, it's going to be abstract because it's inside a interface. Okay. And then we want P. Now normally you would think you would use, interface is sort of like a class, right? So you would think you would use class P on line 6. Class P extends I. No, you don't use it. You use implements. When you're doing what you did, with subclasses, you use extends, but when you're dealing with an interface, you use the word implements. All right. You have basically the same kind of thing here that you would have if I were a superclass. Okay. All right. Now, the X display in P will override the abstract method that is in the interface I. And same thing with the X display method in the Q class. That will override the inherited X display method that's coming from the interface I. Okay, and here we go again. We create a Z array. We create an array whose name is Z, and its type is going to be I square bracket. That's its type. So that means every slot of this Z array is going to have type I. Okay, and then we do our upcasts. The I type is above, right? It's above the P and the Q. Why? Because the P class implements the I interface. Same thing with Q, and the same thing with that. Both P and Q, um, uh, implement the I interface. So the I interface is in effect like a superclass, right? Okay. So those are upcasts on lines 30, 31, and 32. Now we have the for loop. We don't use instance of, and we don't have to use casts on Z square bracket I. Why is that? Well, when the compiler sees Z square bracket I, what is Z square bracket I? What is its type? It's a pointer to a I object if one were to exist. And what does an I object have? Well, it has the display method. It happens to be abstract, but it has the display method. So the compiler won't flag line 35 as having an error, but when you execute it, the X display in the P object and the X display in the Q object will override that inherited one that's coming from the I interface. So you will correctly you will invoke the correct X display method. Okay, so that's another way. I guess this is the fourth way. This is generic for. Fourth way, So the first way was the one way I would not use, because you have to use instance of, and you also have to put cas on z squared bracket I. But all the rest are, ones that are reasonable approaches. Now, another way you use interfaces just to provide constants to the other classes in your program. So here I have interface, my constant, and we have two constants there, uh, rate and min balance. And because they're names of constants, I just by convention I use all capital letters. And I didn't explicitly say this, but they are final and they're also public. So you don't have to say final and public. Final means you can't assign rate. Sort of looks like it might be a variable, right? You can't assign it a new value. And public means it's available to anyone, right? So someone who knows this stuff knows that an interface, if you have some constants, if you're defining something like rate and min balance in an interface, is necessarily a constant and necessarily it's public. So that's frequently the way it's done. So you need to know that, because if you just looked at that, you might think that rate is a variable of type double, and min balance is a variable as well, and it doesn't have public accessibility. Okay, but in fact it does, and there are constants. Okay, and then if you want to use those constants in another class in your program, you just say when you're starting the definition of the class, you say, for example, if you want to create a class U that can use the rate and min balance, you just follow the class name there with the word implements followed by the name of my constants. And then you could use rate and min balance everywhere in that class. You don't qualify it with anything. You just in effect you're sort of the thing which says implements my constants, that in effect is qualifying it. But then when you're actually using rate and min balance within the U class, you don't qualify it. You just say rate and you'll get 7.12, and you say min balance, you'll get 100.0. And you can do the same thing in class V. Just use rate, don't qualify it, use min balance. Okay, so this is very handy. I've done this plenty of times. I want constants to be available in a whole bunch of classes, so I just create an interface up at the top, and then each of the classes just implements that interface, and it automatically gets available those constants. All right, a generic class. Now, this is a new thing. A generic class is a class with data whose type is parameterized. So that means when you create an object from such a class, at that time you can specify what the type of the data is going to be. The data has a parameter associated with it. So when you create the class, you just pass the parameter the type you really want. So it's the same kind of idea with just a regular method that has, let's say, int x as the parameter. When you call it and the argument is 5, the 5 is automatically assigned to the parameter x. That sort of happens. It's the kind of thing that's happening with a generic class. And we did see a generic class, and array lists. That's a generic class. Remember, with array lists, you have to use those weird angle brackets. And when you actually create an object from an array class, uh, you at that time specify uh, the type of the slots that are going to make up the array list. All right, so it's a generic class. All right. So here is, let's see, what is this? Yeah, here is a generic class, right? If you look at line 1, you see the angle brackets T. So T is the parameter. And then I use T wherever I normally would have the type. So X is going to be type T. When you invoke one thing, you're going to pass it something which is of type T. And when you call get, it's going to return something of type T. T is in, for get, is in the position where you're supposed to have the return type. And on line 5, it's in the position which specifies the type of XX. So it's the type that's being used as types are normally used, but it's not the actual type, it's just a parameter. And that thing is going to get replaced when you create the object. So now let's take a look at this program. On line 20, we're creating a pointer, right? We're creating a P1 pointer, and we're specifying that this pointer is going to be pointing to a one-thing object in which T will be replaced with the type integer. Okay, and then on line 21, I'm actually creating a one-thing object. You see, and right there, I'm saying I want T to be integer. So integer is like the argument, and T is the parameter. So integer, in a sense, replaces T. You get a one-thing object from a class in which the T's have been replaced with the type integer. And then we're passing it 7, and the 7 is on line 5 you have a constructor, right? That's the constructor. So the 7 will be received by XX, and that's fine, right? Because 7 is type int, and XX is going to be type integer, and it's okay to assign an int to something of type integer. Remember I spoke about that? You get something called auto boxing when you do that. All right, and then on line 22 we call get, right? The get method in P1 in the object to which P1 points, and it's going to execute the get method on that starts on line 10, and it's going to return what's in X, which is of type integer, and T is going to, for that particular invocation, or for this particular object, the P1 object, is going to be type integer. So it's perfectly legal, right, for the return type to be integer, and the thing that's being returned is because the thing we're returning is type T, right, line 3, and the return type is type T. So okay, so that's all going to, and it's going to be returned to print line. And if you return to print line a pointer to an inner object, it just displays what's in that inner integer object. Okay. And now we're going to do, again, the same sort of thing, but this time the type we want to have are, the type of the data in this one thing object is going to be string. So notice I'm using the angle brackets on line 24 on the left-hand side of the assignment there when I'm declaring the type of P2. And I'm also using it when I am using the new operator to create a new one string object. So that angle bracket string, which follows the new there, that's calling the constructor, and the string is acting like a argument, and it's going to replace the T in the one class, in the one thing class. So the T's for that particular line 24 become string. And so now you have that class that will work with strings, just like the first one, the P1 object will work with integer objects. The P2 object is gonna work with strings, with the string. X will be a string pointer. So you can see the flexibility that generic classes have. All right. Now, one thing you can't do with a generic class is the parameter argument, the argument that's going, the type which is going to be replace the cap T, right? It can't be a primitive type. It has to be a, it has to be a class, all right? And remember I said there's a reason why for every primitive type we need a wrapper class? It's because of array lists, right? Because you can't do that. So you can't create a one thing object in which the inner type there is int. But you can create one in which the type is integer, the wrapper class, right? And an integer object contain an int. So you just use the wrapper classes if you want to have one of these generic uh, classes uh, that hold ints. You just use the wrapper class, so it's actually going to hold integers, things that are a type integer. But you can always access the int within the integer wrapper object very easily, because, in fact, you don't have to do anything really special generally because of auto boxing and auto unboxing. In a previous chapter, we looked at a class called an array list, and that particular class is not in the java.lang package, it's in the java.util package. So you need to import, uh, java.util array list. And if you do that, then in your program, you can just specify the array list without prefixing it with java.util every time. All right, and it has all kinds of good stuff in there, which allows you to do just about anything you would want with that array list. Well, to just show you what actually is inside that array list class, I wrote my own array list class. It's a highly simplified version of the one that's in Java util. So it has very few methods. It's nothing like that one, but it just gives you an idea what's going on when you're using an array list. Okay, and the name of this class is myArrayList. And this is the main method in the program that uses an object that's created from myArrayList. Line 33, I'm creating a myArrayList object, and it's going to have, we're passing integer of that particular type, and that's going to replace T, capital T, which is the argument that that's the parameter that corresponds to this integer argument. So I'm going to get an array list in which the internal type is integer. And the pointer to that myArrayList object will be assigned to OAL. And then I'm calling the add method 3 times. So that statement on line 34 is calling the add method in the object to which OAL points, passing it 5. And that will add 5 to the array list. And that's going to be the first thing. So the size right after line 34 will be 1. Prior to 34, it's 0. Then I add 2 to the next slot, then I add 3 to the next slot. Then I use the get method, and I specify the index when I call get. So on line it's 37, the argument there is invoking get, passing at 0. So it's going to return the pointer that's in that first slot of the array list, which is going to be a pointer to, well, yeah, it's not, it's going to, by the way, I should say that when you do line 34, the 5 is going to be received by a parameter whose type is integer, not int. And so what's actually going into these array slots is a pointer to an object of type int. So when we call the get method here, it's returning that pointer. And if you pass a pointer to an object of type integer, println will display not the pointer, but it will display the integer in the integer object to which the pointer points. So those 3 print lines are going to display the 5 and the 2 and the 3. Now the next slide shows the the actual implementation of the my array list class. And it's significant in two respects. First of all, it really will show you that, a array list in a sense doesn't grow. In a sense, it does grow, but in a sense, it doesn't grow. It definitely doesn't grow in the way you think it grows. The conceptual view is that, you have a certain size, you add something, oh, it gets just one bigger. It actually is not doing that. It has a specific side. And then when something gets all full, then it gets suddenly a lot bigger, so you have a lot more available slots for new additions. That's what's really happening, as you will clearly see, in the next slide, which is also significant in that it's the end of this video series. Wow, you know what this is? This is, actually, I think it is. I think this might be the last slide in this whole series. Yeah, this is the last chapter of the book, chapter 16. And there won't be any video for chapter 17. And the reason why I'm not going to do a video for chapter 17 is because I think it doesn't make sense to actually cover chapter 17. By the way, it's not in the book, but it is in a PDF in the software package. Because if you cover chapter 1 through 16, that's a lot of material. If you have students do a lot of problems, right, and really work with the material in chapter, that's more than enough. And if you get through chapters 1 through 16 in a single semester, you're really doing good. I don't care how smart your students are. If you get through all 16 of those chapters in the book itself, you've really accomplished a lot. And if students have done a lot of assignments correctly and they were able to do it correctly, you are successful. You've had a very successful class. So I think learning this chapter 7 is how to do web programming using Java. And I think that really belongs in a higher level class. Maybe like in my college, we have a web programming class, which is a pretty high level. I think it's, like a senior level course. And there's where you learn that kind of stuff, where, how you could use Java when you're creating web pages and so forth. All right. All right. So what do we got here? We have, as you know, we use the ArrayList class, and I believe that class is in java.util. So if you want to use ArrayList class, you have to import java.util, that package. Now, this is my own ArrayList class, one I wrote, and you can see the implementation. And this is a super, super simplified version of the actual ArrayList class that's in the package java.util. So it just gives you an idea of what's really going on when you're using the actual array list. Okay. Now remember when I said an array will grow? Initially the size of the array is 0. Then when you add stuff to it, it grows to accommodate the size. So you don't have to worry about reaching an upper limit. It just keeps growing to accommodate whatever size is necessary. It could also shrink if you start removing some of the entries. It shrinks. Everything above that just moves down one slot to fill in the vacant slot the slot that was vacated when you removed an item from a slot. Okay. So that's great. On the other hand, an array, arrays are nasty, because if you declare an array of size 90, let's say size 100, that's the size. It's not suddenly going to grow. So if you try to put, when you try to put the 101st item in an array whose length, we don't use size when we're talking about arrays, when it has a length of 100, you want to put in the 101, you're going to get an error message, right? Index out of bounds. Okay, that's what you'll get. So array lists are really great. Wow, they're really great. They grow, and they can even shrink too. And so you don't have to worry about hitting an upper limit. So how the heck do they grow? Well, this is how they grow, and we'll look at the actual code that facilitates the growing. When a inside an array list, you have actually an array. So you got an array list object, you actually have an array inside there. And if you look on line 3, you'll see that I am creating a object array that initially has 10 slots. So my array list actually has inside it an array that has uh, 10 slots to accommodate things. However, look at line 4, the variable size is 0 because initially that array, that 10 slot array, doesn't have anything assigned to it. So we haven't put anything in there, so size is 0, although the length of that object array to which current points is 10, right? So you have length, which is the length of the actual array that's going to hold the stuff that you're adding to an array list. It has a length of 10, although size initially is 0. Okay. All right, then on line 6, we just have, this is a generic class. T is going to be replaced by an actual type when you create a object from this generic class, right? Using square brackets when you invoke the constructor, you specify the type, and then you're going to have square brackets, and then inside the square brackets you're going to have something like string. In which case, string, the type string, would replace the T everywhere in here. Okay. All right. So what does that do? It just returns uh, the thing that's in current I, which is going to be a pointer to whatever object was assigned to that slot. Okay, and that's going to be returned, and T is going to have the appropriate type. It will, in effect, be replaced when when you're creating the object. When you call the constructor, it's going to have that square bracket that has the actual type. Okay, so that works. Now, the really interesting one is line 11, the add method. All right, so the very first thing the add method does is on line 13, it checks the current size, compares it with the current length, right? The size of the array list initially is 0, but the length of the array is 10. So initially, that statement on line 13 is going to return true. You know that true false will return true because, it will return false rather, right? It returns false because size is not greater than or equal to current length, right? Size is 0, current length, the length of the array to which current points. Current, look on line 3, current is a pointer that points to an object array that has 10 slots. So current.length is 10, size is 0. So that true false expression initially is going to be 0. So you don't do the if thing, you just do line 20. And what does line 20 do? It takes what you're passing to the add method, which should have type T, whatever T is, and you're assigning it to a particular slot in the object array. Right? So you're just assigning it to the object array the way you normally assign something to a slot in an array, right? And size is 0, so you're going to assign on the first add, you're going to assign whatever you pass to the add method. You're going to assign it to the very first slot, the slot that has index 0. And then since the plus plus follows the name size, after you use it, use the 0 in it, then you increment it. So the next time you execute 20, you'll be assigning line 20, you'll be assigning X, whatever it is, to slot 1. And then the next time it will be the slot 2, slot 3, slot 4, slot 5, and so on and so forth. So you don't run into anything unusual happening all the way up to the 10th thing you want to assign. When you assign the 10th thing, size, before you actually do the assignment, size is going to be 9, right? And so that's not greater than or equal to the current length. right? You're about to add the 10th element. So you only have 9 in there, right? So the size is not greater than or equal to the current length, right? Size is 9, current length is 10, so 9 is not greater than or equal to 10. Okay. So when you do the 10th add operation, you just do 20. Okay. But then when we do the 11th add operation, you can't add it to this object that you create on line 3 because it has only 10 slots. So what happens is the following. On line 15, by the way, what's pointing to the object that we're using here, the one with 10 slots? A variable called current. That's a pointer. What I want to do is save that pointer. Okay, so what I do is on line 15, I take that pointer and I'm just saving it in a variable old, and it has the same type as current, right? Current has type capital T pointer, whatever T is, and old has the same type. So that's a perfectly legal thing. All right, so now old is where I am saving the pointer to this object that has 10 slots. Then on line 16, I am creating a new object array. And what is going to be the size of the array? Well, old.length, that's going to be 10, right? Because old is pointing to the original array, which has a length of 10. So old.length is 10 plus 50. So what I'm going to do is I'm going to create a new object array, and I'm going to cast it to type, T array. But the array will have 60 slots, not 10. Okay. Then starting on line 17, I have a for loop, and what it will do is just copy the 10 elements that are in the original array to my new array, which now is pointed to by current. So the current now, before we did this rigmarole, current was pointing to this object array that was full that has only 10 slots. But now current array, after we do that for loop, the array current is pointing to has the 10 things in it in the first 10 slots, but it has an additional 50 slots. So it now can accommodate some more additions. So after we do that if statement, then we fall through to 20, which then completes the add. And size goes up to 11, and that will continue to occur until you get up to 60. When you come in that add again and size is 60, that means you got all the slots full. So you then go through this whole process again. You save the pointer to this array with 60. Then you create a new object array, which is going to be old.length. But old now is the one that we were just using that had 60. So that's going to be 60 plus 50, 110 slots. Okay. Then we copy the old one, which has the 60 slots all full, into the new one, which is 110 slots. Okay. And then we fall through to 20 and complete the add. And then we can continue going until we fill up the 110 slots. So that's what's happening inside an array list. So there's actually a lot of overhead associated with an array list. Now, it may not really be much overhead. It all depends on what's the initial size of the object array that we're creating. If the initial size is, let's say, 1, okay, that's not good. Here it's 10. Actually, that's not good because a lot of times you're going to use more than 10 things. You're going to add more than 10 things, in which case you go through this rigmarole of creating a new one and all right. So but if the initial size is large, let's say the initial size is 500, then chances are you're never going to go through that if statement that starts on line 13, which involves a lot of overhead. It won't be much more inefficient. You just come to add and, you just, don't do the if part at all. You just go down to the statement that on line 20, which does the add. So it's almost as efficient as just, assigning something to a regular array. The only time you get inefficiency is if you get this mechanism kicking in, which creates a bigger array and does the copy, and then starts using the bigger array to complete the addition add operation. All right. Now, what is the initial size of an array list? There is some way of specifying the initial size of an array list. Off the top of my head, I don't know how I do it, how to do it, because I never use it. Whatever the initial size is fine for me. If I wanted to, I was concerned about how much time something would take, then I would definitely want to know what that initial value is. If it's really low, I might want to, when I create the array list object, have it start with a much bigger one. So you don't have to do this stuff associated with the if statement on line 13. All right, if I was very conscious about how long it would take, how long the program execution would take. But normally I'll just use whatever the default size of that object is, and if I put in so many things that it has to go through this stuff on line 13, so be it. Program will take a little bit longer than if I gave the object array initially a bigger size, because then I might not have to go through the overhead associated with the if statement on line 13. Of course, if I give it initially a bigger size, if I don't use the bigger size, then I am occupying space that I never use. All right, so there's a trade-off here. If you say on line 3, if you change that to 1,000,000, right? That's going to occupy a lot of space in memory. All right, but then you probably never execute the body of the if statement that starts on line 13. Okay, so you have more efficiency, but you're wasting space. On the other hand, if you use the initial size is going to be 1, the initial length is going to be 1. Then you may be doing, and let's say when you create a new one, you don't say plus 50, you say plus 1, all right? Okay, so the initial length is 1, and when you decide you need a bigger one because you need the current one, you just say, you just create a new array that's just 1 bigger. So then if you needed to do another one, you need to go through the if statement again and again and again every time you want to add a new one. Then you would use only the amount of memory you really need, right? Because the thing would grow, and you would never have any more array slots than you actually need. So there you have, minimum memory usage, but then you have a lot of inefficiency introduced. All right. So I think this is it. This is the end. And I'll tell you, I'm very thankful that we're at the end. It's really hard for me to do these things, and for a variety of reasons. And I'm doing them one after the other. If I were doing one a month, I think it would be better. If I were doing them when I were teaching a class, that would be easy because it would be the material would be really fresh. And then anytime the material is really fresh in your mind, you tend to be more articulate and more coherent in talking about the material. All right, so good luck and keep up the good work. And remember, if you really want to learn something, you got to do a lot of practice. So do a lot of the problems. If you're in the process of taking an introductory course and you're going to take the next one, really work hard on all this stuff, including the chapters on linked lists and recursion, and then you'll be a star student. I can almost guarantee it in the next class. And then, the next class will be easy. What's really good is that if you in the first class can get momentum going, then that momentum will carry you into the next class, the next higher up class, and then and you do really well in that one, and so then you get the momentum continues. It carries you through your entire undergraduate career. If you just can start it with the very first one, uh, then you do really well in the second one, which means that you'll be able to really do well in the third one. And then when you get a job, you'll get a good job because you'll have a great cumulative average and you can get great recommendations, so you'll get a great job. And then you start working and you do really good work, so you get promoted and you keep doing it. You ultimately end up being the president of the United States. So it all starts with, going through this course very carefully and doing a lot of problems, and you might end up being president of the United States. There you go. All right. So good luck to you, and be well.